I'm actually giving a board talk, so if I can share my screen, I'll just do it.
Let's prepare it.
Just a second. Okay.
Okay, good morning everyone again. Today, inshallah, I will give you the class instead of Dr.
Now we are ready. We can start. Thank you.
So good morning, everyone. Today we are going to start first session, morning session from the SIMPA school. Today we start with a talk of Prof. Adam. The talk is called Factoring, Octonion Polynomials. Okay, Prof. Adam Chapman, you can start, please.
Thanks. So, hello everybody. It's good to see you, even though it's virtual. Okay, let's start. I know that there are some students and also some people who don't specialize in Octonion, so I'll give some brief introduction. Many people are familiar with this family of algebras. So you start with the real numbers, which are contained in the complex numbers, and in turn they are contained in Hamilton's quaternions. But not so many people are aware of the fact that Hamilton also came up with the construction of the octonions more or less at the same time. So I'll give here some brief introduction of how to construct these, also over arbitrary fields. The only assumption I'm going to use is that the field F, so F is a field, and I want it to be of characteristic different from 2, which is not necessary in general. Like, you can repeat the same construction also for characteristic 2, but for this talk, for simplicity's sake, I'm going to assume the characteristic is different from 2. So you want a quadratic field extension of F. So what do? You pick some alpha in the field, which is non-zero, and then you look at K, which is constructed by adjoining some I, satisfying I squared is alpha. So this is either a quadratic extension of F or an étale quadratic algebra over F. So it's an étale quadratic extension of F, and it's equipped with an involution, which is the Galois automorphism of this extension, just mapping I to negative I. So in characteristic 2, it would be different. So that's our sigma, and it gives rise to some norm form from K to F, mapping every Z to sigma Z times Z. Now the question is how to keep on going and constructing larger and larger algebras. So you pick another element, B or beta. You take some beta in F. And now you construct an algebra Q by taking K, direct sum K times some J. You want this algebra to be associative. And then J squared to be equal to beta, and J inverse to be sigma Z for any Z in K. And that's what we call a quaternion algebra. So Q is a quaternion algebra. And it's usually denoted by what we call a Hilbert symbol, alpha beta over F. Okay. So this is a non-commutative but associative algebra. It can be either a division algebra or a 2x2 matrix algebra over F. It mainly depends on the norm form. So here again, the involution extends from K to Q by just mapping J to negative J. So every A plus bj plus ci plus dij is mapped to A minus bj minus ci minus dij. And again, you have a norm form here from Q to F, mapping every z to sigma z times z. This is a quadratic form of dimension 4 over the base field F. And the algebra is a division algebra if and only if this quadratic form is anisotropic. If it's isotropic, meaning if it has a non-trivial zero, the algebra is just the 2 by 2 matrix algebra over F. But you can repeat this process. So this is called the Cayley-Dickson process, and it can be repeated. This is essentially the Cayley-Dickson process, and it can be repeated any number of times you want. The next step is the most crucial. So you pick some gamma in F again, and you look at some algebra A built over that Q that we constructed earlier. So it's Q plus Q times some L. Occasionally they take K instead of L, but K is also occasionally referred to as I times J in the previous algebra, so I prefer to take L. And now you should be careful a little bit with the multiplication table. So let's see if I remember it correctly. You take Q plus RL times S plus TL, and you need to get an element in A. So it should be something plus something times L. And the formula is QS plus sigma T R times gamma plus, now it's TQ plus R sigma S, all that times L. So it's a bit strange. This is actually the proper formula for the Cayley-Dickson process. It applies also in the earlier stages. That's just there. The previous algebras were commutative, so it doesn't really matter whether you write things in this order or not. But here Q is not commutative anymore, so when you construct the following algebra, the Octonion algebra, you need to be careful about these things. So in particular, L squared is gamma. And this algebra is denoted by this extended idea of a symbol algebra, alpha, beta, gamma over F. And this algebra is special in several different ways. So first of all, it's not associative anymore. So it's not associative. It's alternative. And what do you mean by alternative? So alternative algebra means that every two elements in the algebra live in an associative subalgebra. So every two elements live in an associative subalgebra. And in that respect, it's already special, because you have a family of alternative algebras. But if you want only simple alternative algebras that have no proper two-sided ideals, then apparently you don't have so many of those. You have either associative algebras, in which case these are simple associative algebras for which we have a structure theory quite well studied, and octonions. So apparently by Kleinfeld's theorem, by Kleinfeld's theorem, every simple alternative algebra is either associative or Octonian. I didn't mention, I mentioned it while speaking, but this algebra is what we call an Octonian algebra. So these Octonian algebras are special also in the world of alternative algebras because all simple alternative algebras are either associative, for which we already have a structure theory, or Octonians. Octonians are special in that sense. If you want an example for this construction, then if you take F to be the reals, and you take alpha and beta and gamma to be -1, then this algebra -1 over the reals is Hamilton's quaternions, and -1 over the reals is Hamilton's octonions. Okay, now this Cayley-Dixon process can be repeated to construct larger algebras, but apparently they are, I wouldn't say not interesting, but not as interesting as these algebras, because there's another feature to these algebras, which is due to Hurwitz, all composition algebras, which I'll explain in a second, are either quadratic et al. Which is the first case we mentioned. It's basically a quadratic field extension of the field. Quaternion algebras, or Octonian algebras. So these give you dimensions 2, 4, and 8. Now, what do we mean by a composition algebra? I'll mention briefly. So it's an algebra equipped with a quadratic, multiplicative, non-singular norm form. Okay. So all these algebras are equipped with a norm form. I didn't mention here, but the Octonian algebra that we construct here has a norm form. First of all, it has an involution mapping any Q plus RL to sigma Q minus RL, and the norm form again from A to F maps every Z to sigma Z. So it has a norm form, and you can repeat this norm form also for the larger algebras, but they are not multiplicative anymore. So the funny thing is that it stops being multiplicative here. For the next stage, it's not multiplicative. You can have two elements, both of non-zero norm, and the product can be 0, which is definitely of norm 0. So it stops being multiplicative here, and that's another reason why these algebras are interesting. So I think that's probably enough to say about Octonian algebras. In general, there are many other interesting properties of these, connecting them to Lie groups of type G2 and so on. But now I want to talk a little bit about polynomials. So what are Octonian polynomials? Why do we care about them, and how do we study them? So one of the features for Octonian algebras and for algebras in general is how they behave under central extensions. So if you have an Octonian algebra alpha, beta, gamma over some F, and you have a field extension E over F, so it's a field extension, then you can study this tensor product which gives you a new, somewhat larger algebra by extending the center. And the way to make it generic is to consider polynomials. So especially if you focus on simple field extensions, then you can take the tensor product with the ring of polynomials over F, and that gives you a new algebra. So this alpha, beta, gamma, but over the ring of polynomials. And that's what we call the ring of polynomials over A. Okay, so it's a crucial point. Our X, our indeterminate here, is central in the new algebra. So in many cases, you would expect the indeterminate to be an arbitrary element from the algebra. An arbitrary element from the algebra is not central. But here, when we talk about polynomials, we consider X to be a central element. So notice that. X is central in this guy. And now we want to understand how these elements behave, how the polynomials in this new ring behave. So first of all, how do they look like? You can take an arbitrary element, which we denote by fx usually. I'll explain in a second why. And since x is central, it's also in the nucleus of the algebra. You can express every polynomial in this way. So it's an times x to the n plus whatever you want to a1x plus a0 or a0. Well, these coefficients, they all live in A. The moment you have a ring, and this ring is it's not division algebra anymore, and you want to understand how it behaves, one of the first things you do is to try to break it down into indecomposable bits. When we talk about polynomials, hopefully you can break any given polynomial down into linear factors. So how do we break this down? How decompose this polynomial into linear factors? Apparently, and this is a theorem that I proved, but I cannot guarantee that it did not appear elsewhere. So it is possible that somebody noticed that already for Octonians. I just didn't find it in the literature. So theorem that I want to mention now is that you can factor a linear bit from f. So f is equal to g times x minus lambda if and only if f lambda is 0. And what do we mean by f lambda? When you write down the polynomial this way, you can plug in lambda. So this is well defined. It doesn't mean that you can plug in lambda in any form of the polynomial, because you can also place x on the left-hand side of the coefficient. But if you want it to be well defined, you need to decide where you place the x's before you plug in any variable, because again, lambda doesn't have to be in the center. Okay? So I'm plugging in lambda only after I put all the x's on the right-hand side. So I have an lambda to the n plus whatever plus a1 lambda plus a0, and that has to be 0. So apparently, and it's not so difficult to prove. Thing is that if you, so I'll call it a proof this way. So it's not a proper proof. If you want to read the proper proofs, you need to go to read the paper. But the idea is that if you only take some coefficient, let's say ak and x to the k, and you subtract ak times lambda to the k, then since x is central, you only have two elements here that are not coming from the center, ak and lambda. And since the algebra is an Octonion algebra, these two elements live in an associative subalgebra. And then you can treat this formula, you can treat this expression as if it lives inside an associative world, and then you do whatever you know. You just can put the ak outside, and then you have all this game of proper, oops. And then x minus lambda. So you can do that for every coefficient separately, and then you show that you can pull out x minus lambda from the expression fx minus f lambda, but f lambda is 0, so you can conclude the theorem that I mentioned above. So the moment you have a lambda that satisfies this thing, I give it a name, and the proper name for that would be a root. Okay, so the definition is that lambda from A is a root of fx if f lambda defined the way I defined it 4 lines ago equals 0. So what's the conclusion? The conclusion is that you can factor x minus lambda from the right, not from the left, only from the right. You can develop an equivalent theory for everything, placing all the x's on the left and then factoring from the left. Let's put that aside. But you can factor x minus lambda from the right if and only if this lambda is a root of f. And now, if you have an algorithm for finding roots for f, you can keep factoring again and again, because now you have g. And if you can find the roots of g, you can factor another thing from g, and then you're left with a smaller polynomial. You can repeat that till you get a full factorization of the polynomial. Before I proceed, I want to say one word about Wedderburn's decomposition method. So if there's anybody here who is familiar with polynomials over associative division rings, then you probably know about Wedderburn's decomposition method, which basically gives the full factorization without the need to repeat it for the lower polynomial. So for associative, I'm opening a window here. It's not directly connected to the rest of the talk, but for associative division algebras, if mu and lambda are roots of fx, then mu minus lambda times mu minus lambda inverse is a root of gx, where fx is equal to gx times x minus lambda. So this is called the Wedderburn's decomposition method. But it doesn't hold for Octonions. I can give counterexamples. So it doesn't hold for Octonions. It's really a shame, but that's the situation. The good thing about this method is that if you have a set of n distinct roots for a polynomial of degree n, you can use this method to just get a full factorization into linear bits. You cannot do that for octonions. Unfortunately, you have to study the roots of G again after you factored x minus lambda from it. So that's how it is. Still, if we have an algorithm for finding the roots, then we're done. Computationally, it may take some time, but at least you can give the computer the job of finding all the roots and factoring the polynomials. So the main question now is how to find the roots So it's a legitimate question in its own right, how to find the roots of a given polynomial. People have been working on that over quaternions already before, and apparently the trick is not so different. So what do? We have fx in this algebra. And we construct a polynomial that I would nickname the companion polynomial of f, so cfx, which is going to be defined, so that's definition, to be sigma fx times fx. So since it's a central extension of the Octonion algebra, the sigma extends naturally to ax, and it behaves in essentially the same way. So you have a center, which is the ring of polynomials over the original field, and the moment you multiply sigma of a polynomial times the original polynomial, what do you get? You get a polynomial over the field. So if you want just to get some understanding of what's going on here, so if here the polynomial is an x to the n plus whatever to a naught, then here, what do you get for the highest coefficient? You just get sigma an times an, which is, so that's times x to the n. This thing is the norm of an, which definitely lives in the field. Then the next coefficient would be sigma an times an minus 1 plus sigma an minus 1 times an, and that's the trace. Well, I haven't defined what the trace is, but the trace is another part of what you get in these algebras. It's essentially the, in characteristics are different from 2, it's 2 times the projection on the central component of the element. But anyhow, this is the trace of sigma an times an minus 1, and so on. So all the coefficients live in the center. Why is that good? Suppose we are not dealing with arbitrary fields. Suppose you are dealing with the real numbers, and your Octonion algebra is Hamilton's Octonion algebra with the symbol -1, -1, -1. I don't have a clue how to solve an Octonion polynomial, but I do have many tools for solving real polynomials. So most of them are numeric. That's okay. But still, we have many tools for solving real polynomials. And it's good to be able to translate the problem from Octonion polynomials to real polynomials or to polynomials over fields. We understand fields better than Octonion algebras. Now, what's the connection between these two polynomials? So I have this fx, and with which I construct this cfx, and I want to solve this polynomial, to find the roots of this polynomial, to somehow go back to fx. So here's the main theorem. The main theorem is that every, well, yeah, I'll put it this way. So one thing is that all roots of fx are also roots of c fx. So that's one thing. And the other thing is that every root of c fx is a conjugate of some root of fx. So eventually, what I'm trying to say is that the roots of CFX are the conjugacy classes of the roots of f. So what you can see here is that since CFX has only central coefficients, it cannot tell which field extension of f you live in. Okay, when you take an Octonion algebra, you have f as a base field, but in between the Octonion algebra and the base field, you have infinitely many different quadratic extensions of f living inside. So if you have the Hamilton's Octonion algebra over the reals, you have infinitely many copies of the complex numbers inside, but you cannot tell which field you're coming from. So they are all legitimate roots of CFX. On the other hand, is that if you take an element from CFX, you can find some friend of it, of his or her or it, who is a root of the original polynomial. So that's the main thing. In short, the roots of CFX are the conjugacy classes of the roots of fx. Now, suppose you know how to find the roots of CFX, which is something you are able to do if you live over the reals. If you start with the reals and you construct the usual Octonion algebra over the reals, you take a polynomial over the Octonion algebra, and you get from it this companion polynomial over the reals. Or you can find all the roots of this polynomial, because this is an equation of the complex numbers, and you can find them at least numerically. So suppose now that that you solved, that you found the roots of this guy in A. Well, suppose you could do it. They are grouped into conjugacy class, so take one conjugacy class. What do we mean by a conjugacy class? So if you have an element in an Octonion algebra, then it has a trace and it has a norm. If you have take a z, then you have this norm that I mentioned. It's sigma z times z, and you have the trace, which is sigma z plus z. So let's just write them down as n and t. And all the elements in the conjugacy class of Z are characterized by the equation Z squared minus t times Z plus n equals 0. So now you want to take this conjugacy class of roots of CFX and to reconstruct the root of fx from that conjugacy class. How do you do it? So you have, so we want to find the lambda in this class that satisfies f lambda equals 0. So just use the identity lambda squared minus t times lambda plus n equals 0 to reduce it to a linear equation. So you have lambda squared minus t times lambda plus n equals 0. You can isolate lambda squared. So you have lambda squared is t times lambda minus n. So anytime you have the power of lambda here, which is larger than 2, you just reduce it to 1 power lower by plugging in this thing. T and n are central, so they don't interfere with anything. They don't bother you at all. You repeat that any number of times you need to reduce it to a linear equation, so you end up with some e times lambda plus g equals 0, and then lambda is negative e inverse times g. So this is the unique root of fx from this class. Now you can have a small problem. You can have a problem if this e is 0. But apparently it's not a problem. If that happens, all it means is that the entire conjugacy class consists of roots of the original polynomial, which can happen. So you can have either a single root from that conjugacy class, or the entire conjugacy class is in the set of roots of the polynomial. So that gives you an algorithm for solving any given polynomial equation. And then you can factor any given polynomial into linear factors. Just to give a very simple basic example, just so that you, well, I'm not going to do all the algorithm. I'll just give the easiest example I can come up with. So if you take your field F to be the reals, and you take your algebra A to be this Hamilton Octonion algebra, and your polynomial, let's say, is x minus I. X minus I has a single root, which is I. Okay, if you plug in any other element, you get something which is non-zero. But if you take CF of x, CF of x, then it's sigma fx times fx. Sigma fx here is x plus I, and then you multiply by x minus I, and you get x squared plus 1. Now the roots here it's only I, and here you have all the AI plus, well, actually, it's infinitely many, so all the conjugates of I. So it includes J, it includes K, it includes L, it includes I plus J over square root of 2, and so on. So yeah, so that's the algorithm, and I think that's enough for this. In the remaining of my talk, the remaining time of my talk, I want to say one word about why I called it the companion polynomial, and it's connected to eigenvalues. So how are we dealing with eigenvalues here at all? So eigenvalues, or the connection to eigenvalues. So if you take an Octonion algebra A, you can think about the algebra of n by n matrices over A, defined in the usual way, the same multiplication rule, the same addition, of course, it's slot-wise. And you say that lambda is a left or right eigenvalue of B if there exists a non-zero vector for which B times this vector is lambda times this vector, or B times this vector is this vector times lambda if you want to write eigenvalue. So these eigenvalues are pretty difficult to compute. Okay? They're even difficult to compute for quaternions, but they're even harder for octonions. At least for quaternions, we have some results. For octonions, we have nothing, essentially. But for a very specific matrix, we do know how to compute the eigenvalues, or at least some of them. So given a polynomial fx, given a monic polynomial, so here we want it to start with x to the n, and then you have a minus n minus 1 x to the n minus 1, so on. We construct the companion matrix, CF without an x, which is defined in the usual way. So it's the companion matrix as you would define it for fields. So you have 0, 1, 0, 0, 0, 1, 0, so on. And at the bottom you have negative A0, negative A1, all the way up to negative an minus 1. So this is an n by n matrix over the Octonion algebra. And apparently the right eigenvalues of this companion matrix are the same as the roots of the companion polynomial. So this is a theorem, it's not a trivial theorem. They contain the left eigenvalues of this guy. So it's a one-sided inclusion. It's not a two-sided thing. It doesn't go in the other way. And that includes, and again, it's not an equality, it's just an inclusion. It includes the roots of fx. Which is cool. This was known more or less for quaternion algebras, but for quaternion algebras here you would have an equality. But for octonions you don't have an equality here. So this bizarre set behaves slightly differently in the case of octonion algebras, of octonion polynomials. And just to perhaps give a quick example, then if you consider the polynomial x squared plus ix plus ij plus 1 over Hamilton's quaternions, then j is not a root, but it is a left eigenvalue of CF. So funny things happen for octonion polynomials, and now I have more or less 10 minutes, so I won't use all of them. I just want to say 2 words on open questions. There are some students here, some of which would be happy to have interesting master's projects or PhD projects. So what are the open questions I can suggest in this direction? So one option is to try to find roots of higher Cayley-Dickson algebras. So find the roots of polynomials over higher Cayley-Dickson algebras. Now, it sounds like you know, like an ad hoc question, but it's not. So apparently I found some papers in physics that reduce questions in ideal fluids to polynomial equations over the Sedanians, for instance. So it's not useless. Of course, the Sedanians are not as interesting as the Octonians, but if you have reasons from physics to study them, then why not? So that certainly is a worthy goal. They are a bit tricky because you cannot use, they are not alternatives, so you cannot use many of the results we have here. They're not a it's not a composition algebra either. So there are some issues, but still I think it's something that somebody should try to do. And find the left and right eigenvalues of an Octonion matrix. So I should mention a little bit what we know here. So for quaternions, we have a method for finding the right eigenvalues. We don't have a universal method for finding the left eigenvalues. We have only for 2x2 matrices. For 3x3, there's something, but it's not really substantial. For octonions, even right eigenvalues are a complete mystery, unless you consider those companion matrices of monic polynomials, for which I know what the right eigenvalues are. Otherwise, it's a completely open question. And yeah, I think that's enough for today. So thank you.
Where is
Questions, please?
Any questions?
Okay, any questions? So if there is no questions, thanks to the speaker.
Hello?
There's somebody.
Yes.
I would like to ask one simple question, maybe.
Yes.
We have formal definition of derivative for a given polynomial. So
Yes.
my question will be, do we have any kind of analogs already known for Octonion polynomials relating polynomial and its derivative? Like Gauss-Lucas theorem, for example, which tells us about the location of roots of derivative and many other related statements. This will be interesting to check for Octonion polynomials. I don't know, maybe something is already known.
Yeah, that's a good question. I didn't check it in this direction, but I was studying a little bit the dynamics of Octonion polynomials recently, and we were trying to see how because you can define it formally, right? You can,
right, yes.
Yeah, you can just consider x as a central thing, and then the derivative is n times x to the n minus 1. But apparently these formal derivatives, they don't give you so much information, at least as far as I could find, but it could be that they give you other pieces of information that I was not looking for. It's a good question, though.
Yeah, but such simple questions as existence of any analogs of Gauss-Lucas result about location of roots of derivatives in the convex hull of zeros of polynomials. So
yeah, I can add it to the open questions if you want. But it's a good question. You're correct. It's at least one should check the literature and see if somebody has done it already or not.
Yeah, but could be of some interest. And another question is, since we have a relation with eigenvalues via companion matrices, we could look for stability theory. Like we have different notion of stability for polynomials and for matrices. Like there are no eigenvalues in the left half plane, and we know we could have similar analogs for Octonions, and it looks like the whole theory of stability is open for polynomials over Octonions.
Yeah, and then you can translate probably many results using this. Yeah.
Yes, and these are really practical questions because stability theory is describing resonance phenomena and other well-known practical phenomena, and who knows, maybe Octonion polynomials describe it better, at least for some particular situations, so on. Yeah. Just to add one more question. Thank you. So, but really interesting. Thank you for it. Was very interesting talk. Yeah.
Thanks.
Okay, thank you for the speaker for interesting talk. If no questions, we thank one more time to the speaker. So now we have 3 minutes break, then we can continue our next session. Thank you.
Thanks.